Sijs. I work with TNO, a research institute in the Netherlands. The kind of applications that we work on, if you consider robotic systems, are those two that you see over here. Well, that's now not yet robotic, but on the one side, in the Netherlands, if you look at the Dutch MOD, divers are sent into the minefield to detect and neutralize mines so that ships can sail more safe. And on the other one here, we see also, which is another application, it's on intelligent vehicles or autonomous vehicles. Well, in this case, you're still driving the car yourself, but hopefully in future we can arrange some things that it will be more automated. Well, first some things of TNO. So TNO is a research institute. Typically people don't know what TNO is because the Netherlands is a small country and there's only one actual research institute, that's TNO. There are three, but TNO is the biggest one. But we kind of like to compare ourselves with Fraunhofer in Germany or with CNRS in France. I've looked up something in England, but in England it's not so much like one national research institute on applied sciences, but it's more or less related to that field. We have around 3,500 people. And the majority has a master degree or a PhD. It's also interdisciplinary. So we have people with background from the alpha, the beta, or the gamma studies. But also, if you look at the applications, there's a large variety. We work on logistics and transportations, on the defense and security. We also work on ICT-related topics, so telecommunications, and also on the circular economy, so that you look at the entire life cycle of your product. There's one that I forgot, which is healthy living. That's the bullet that I forgot. So we also work on healthy living, not on the drugs and diseases, but more on whether you have whether your working environment is proper enough, so regulations. Now, robotics and real-life operations, and what are we talking about? We are not talking about the industrial applications, like you see these big factory halls with a lot of robotics arms, manufacturing cars. That's not what we are talking about. We are talking about robotic systems in harsh conditions. It's not only harsh because there's a mine over there, but it's also harsh because there's no GPS underwater, so you cannot locate yourself that well underwater. Also, communication doesn't work, so you can communicate, but it goes acoustically, which is as if we would be back to the 90s in bandwidth. Also, we are talking about real-time robotic systems, so the next action, for example, the throttle or steering, should be done in the next 0.1 second. The next maneuver, so either lane keeping or lane change, should be computed every second, and it should be readily available. It cannot be the case that no action has been computed, because then the system doesn't know what to do, and it will not behave properly. Also, if we look at this man-machine teaming, which you see over here with a guy in a wheelchair and a robotic arm, that's the very simple one, man-machine team. What we are looking at for far more complex and interactions. The current stage of robotic systems is that they are special purpose, so they can do one task, and they can do that task very well. They work in a static and in a predictable environment, like the factory plant. They typically work solitary, so you give them a command, they do that, and then they'll come back to you and say, what do I have to do next? But that's the only interaction that you typically have with them. And they also operate in non-critical conditions, so gaming or manufacturing. Hopefully in future we can change that, and we can make systems, robotic systems, that have a general purpose. So it cannot do only one task, but multiple tasks. And if you give them a new task, they can understand what that new task would encompass. Also, that they can go out in a dynamic and an unpredictable environment. That they can be really collaborative with humans, being a user or an operator or a team member, and they can also work in critical conditions. And that's for the robotic system in the future. We would like to call them more autonomous systems. That's the term that we use at TNO. So our vision is that we want to develop systems that have a general purpose, that have a profound interaction with the user, and that they can handle the open world. I'm not alone on that topic, so I have two of my colleagues also here now. So Willeke will give a talk tomorrow with more details on how we develop a Grakn kind of solution on whether the system is capable of doing a task or not. And Fieke is presenting in the afternoon. Not sure whether the 4 o'clock is still right because there's some change in the schedule. But that will be on whether it can learn or not. My talk will be on the robotic case itself. I will give also some introduction on how we use Grakn, how we model the external world, the internal world, and so on. First, a bit of a personal background. So I work in the Department of Acoustics and Sonar, but my main technical efforts are in the field of autonomous systems. Part of that is the hybrid AI, and we call it hybrid AI. And what we mean with that is that we want to have the data-driven AI kind of solutions with the knowledge-driven or the model-driven AI solutions, and we want to combine those two. Also, the applications that I work in are the mine hunting and the surveillance or the search cases. We have these kind of robotic systems to our disposal, so we have flying drones, big, small ones, and we have these kind of vehicles for scanning the seabed. On the other hand, I also have a position at the TU Delft, and there I work on robotics as well, with some PhDs and some masters, and we work on more toy examples, so these kinds of robotic cars. I try to combine the two by using the same tools. So frequently what we are using is ROS and Python for coding, Gazebo, which is a 3D simulation environment. You'll see a picture of that. We use Ubuntu as an operating system, and as of recently, 1-2 years, we're also using Grakn to give the system explicit knowledge. So throughout this talk, I will cover these topics. So going towards real-time autonomous systems, rather than a batch database kind of system. A robotic system or a system that is knowledge-centered, and that's where all knowledge is hard-coded by engineers in all sorts of software routines throughout the systems that you cannot really grasp. And that it's proactive in its capabilities, rather than reactive and it doesn't know why it cannot do a particular task. And I also have some videos to keep you a bit awake. So, a real-time autonomous system, what do we think of that? What it is? Well, it's a system that can receive a task. For example, search, profile, warn, and within some constraints that, as a user or as a user you can define, is free to choose how to execute that task. So here we have our autonomous system, and it can either have a search, a profile, or a warn task, and it also has sensors, signal processing routines, to get some external awareness. How does the world look like? And we also want to give it some internal awareness. So am I still operating properly or not? Classically, so we always considered only this part here. If I know my world as good as possible, I will be able to execute my task as good as possible. Well, recently we also are trying to cover this part here, also using Grakn. One thing to take is that this search, profile, and warn task can have different meaning depending on your external environment. So if I have to search for a car, I will do it differently than if I have to search for a cat, for example. So the context in which you are receiving that task will also determine how to best execute that task. So how do we typically develop a robotic system as a functional setup? So here we have the environment in which the robotic system is in. It can have some sensors like a GPS camera and the LiDAR. That sensor signals are being processed by some Python code software routines to give some external awareness. And that the output of those routines, for example, detection algorithms, detecting people on a particular location, is being stored in our external state, representing how the system observes the world or perceives the world. That information is going into the external planning routine, which is receiving a task and its constraints. And based on some planning methods, it can compute, in this case, a waypoint for the autopilot and a viewpoint for the camera pilot. And that is being executed then in the real world. And then you have this closed loop, because if I change my viewpoint or if I change my position, I will also change my sensors, signals, so therefore I have this loop, and this loop is called a control loop. Now as an example, so if we take, for example, a flying drone, then we have the same sensors, the same actuators. This is what we call actuators or controllers. We have two awareness routines, like an object detection algorithm, which are abundantly available. And also we have a routine that keeps track of where we went to see what area we were covering. So in that sense, you would have some kind of an external state that looks like this, where the white line is where you were flying, the dark green is the area that you've covered, and the yellow dot is a detection that you've made, in this case of a QR marker. Then that information is headed towards the path planning, which, depending on what it needs to be done and what the constraints of the area is, computes the next 10 seconds of paths for the drone to fly. Now we also implemented this, and we also do real-life experimentations. So in this case we had 3 drones, 2 for doing the search, 1 for doing identification. So the area was divided into 2. One drone, each drone got a particular section of the area, flew over it, and in case of a detection, like this QR marker, the identification task was sent to the 3rd drone, resulting in a video on that. So here you see the field that we were searching. We are standing over here with our 3 drones. This is one of them. That's the marker that we were looking for. I didn't make a video, by the way, but I'm happy that someone did. So the 2 drones are start flying, and they will start to fly their trajectory with high altitude. And at some point the marker is being detected, and the 3rd drone is getting the task, not by us, but by the system itself. So we didn't do anything, we just were with our hands crossed behind our back the whole time. And this 3rd drone is then going for a close-up to do the profiling itself. And these are our toy drones. We also have bigger drones, but these are the drones that are allowed to drop from the sky when something happens. So we always have those spare ones. Now we did this without having a centralized knowledge base. So all stuff was hard-coded throughout the entire system, based on assumptions, based on if-then rules, based on whatever. So for example, we use the QR marker, but the system doesn't know that it can only detect the QR marker, but I, as a system engineer, made it that way. But the system itself doesn't know it. So if I ask, say, can you detect a cat? It doesn't know that it cannot detect the cat. Also, it doesn't know on which background this detection algorithm will work. So I developed it in such a way that it will work on grass fields, but if it's on a pavement or something, it might not be able to detect the QR marker. But it doesn't know it. I hard-coded that into the detection algorithm, or that's the way I tuned it. Also the path, it's a lawnmower pattern, which I just decided to take a lawnmower pattern. And with a particular cruising speed, also the camera aperture and the height, both of them defined the distance between those legs if I want to have full coverage. That's also something that I, as a system engineer, designed it in such a way that it all comes together in this one task, in this one situation. And there's all sorts of implicit knowledge hard-coded throughout the system. And if I want to go from a system with a special purpose to a general purpose, I want to be able that the system knows what aspects I designed for that purpose, and that it's be able to adapt that in case it needs to detect at a different height. So there we started to go to a centralized knowledge base, and also some knowledge modeling of the external world. We use some knowledge reasoning to have those parameters and those models fed into our to the software routines that we already have. So basically what we do is the classical way is that this part of the system we call automation, and if we want to have really an autonomous system, we need to have such a centralized knowledge base so that the system itself can reason on what to do and when to do and where to do and how to do. Now this complex, well, this implementation picture is often more extracted even into functional components. So we have our sensors, we have some basic filtering like frequency analysis or something. We have awareness routines to process the filtered data. Normally, we would not consider those databases, but we immediately go to planning and control. That's the classic control loop. And what we basically did is we included this DIKW model, so the data, information, knowledge, and wisdom. But we have no idea how to do wisdom yet, so we just started with knowledge as that. And the tools that we are using are here on the right. So at this low level, we either go to the real world or to a simulated world. We use ROS and Python for the automation part, and we use Grakn, KGCN, and Python because we often have to do still number crunching on the knowledge level. Now, just to give an example, which is actually our first experience with Grakn. This is this 3D simulated world that I talked about, gazebo, where we have a compound, where we have a village and a road. There are objects on the road, which are cars. These one I just copied in. Those are not the real cars in that one. And what we wanted to know is whether a car was threatening to the compound or not. That's basically the question that we have. When we started to modeling this use case, we saw we have an entity, which is a compound. We have an object, which is also an entity. And we have a relation between those two, which is a threatness relation, and it has a particular threat level. So that's how we started, and we more or less constructed a high-level ontology or a schema that looks like this. So we have entities, physical concepts. We have the environment, and the compound is a particular environment. And we have objects, and objects can be a vehicle, and a vehicle can be a bicycle or a car or a bus or whatever. Now, this object has a threatness relation to the compound, and also, of course, a threatness relation to any other object. And it also has properties. So, for example, the compound has a pose and a vulnerability. Not sure whether you can read it, but I can read it. And the object has a position, a speed. It has impact powers, so it can attack with a particular force or not. So if you are a truck, then you have more impact power than if you are a bike. But each object also has a particular vulnerability. And then this threat relation also has attributes, which are distance, approaching speed, and threat level. So this was our first use case of trying to use Grakn in a way that Grakn was should be used. Well, should be used, can be used. And we started with the first schema. So these are just the concepts that we have, the objects, the compound, the vehicles. We also have actors, which can be our system or can be a human. And we also have physical components like the camera and the LiDAR. And we will have in future also relation that the autonomous system, which we will call the Husky, is equipped with cameras, LiDARs, and so on. So there will be all sorts of relations over the place, but this is just the concept itself. Now focusing on the threatens relation, so the autonomous system and the bicycle, two objects, have a threatens relation, and that has an approaching speed, a distance, and a threat level. And now the trick is that, because that's in this real-time system, that these values need to be continuously updated once you get new sensor data that is being processed and so on. And that was the trick. So the trick was not yet the schema, but the trick was the instantiation of the data and the processed signals or information. So for example, we have our autonomous system, again, which is with its camera recording a particular scenario. We have a detection algorithm which is detecting a bike and a person, and that's going to a tracking module that keeps track of that bike and that person every 10th of a second. Once it spots a new object, it will instantiate that object into the Grakn key space, also instantiating a relation over there, and also estimating the speed of all those objects, so you can also compute an approaching speed and a distance between two objects. Then we have a threat assessment, but you can have any assessment, a behavior assessment or a kind of assessment you want, which basically queries for all these values and with some properties of the objects like impact power and vulnerability and so on, computes a threat level. And this is basically the interaction that we always have between the Grakn key space on the one hand and our Python number cruncher modules on the other hand. And a big challenge for us was the speed of this interaction. So this would give results every 10th of a second, but it's really too slow to put at 10th of a second all these things into Grakn, query for them, and put back a threat level. So we found it out a bit the hard way, but this is still our ideal picture. So these more or less cover the first two topics. So going towards a centralized system that is interacting with all the sensor data and all the process sensor data that it is running within that system, and combine that with some kind of an ontology or a high-level ontology or a schema on how to represent the outside world and get a picture of how the situation looks like. Now, the second part of my presentation will be on this proactive capabilities. And that's where, as a system engineer, you are developing the system. And you know, for example, that I'm developing a system for two tasks, for a search task and a profile task. And I will only focus on the left part of the system, so only the observation perception side of the system, not the planning part. But also for the planning part, you will have you can do similar stuff. As a system engineer, I know whether my system is capable of doing that task or not, because I've constructed all these modules and all the software routines in here. And I want to give that information to the system in some way. So I picked out the two tasks, search and profile. And as an engineer, you say, okay, if I want to do search, I need to have a particular scanning configuration. And that scanning configuration is positioned over here. It's just saying I have a configuration of software routines in order to process my sensor data into the object detection that I'm interested in. I also have an area coverage planner, which is on the right side, which plans so that I will search the entire area. Now, the scanning configuration requires a LiDAR and a GPS sensor. It doesn't require any camera, for example. That's relevant. For the profiling task, however, it's a bit different. There I have a sketching configuration, which is also on the left side here. And that requires a camera and a GPS. And it optionally can be using a LiDAR or not. Now, if I would develop such a system, then I would say, okay, you have to do two tasks. You have a scanning configuration and a sketching configuration, and I will invoke both on the left side. Independent on whether that system is even doing the profiling task, it will still run that entire configuration. And that's a bit of a waste of resources. So we try to make that more online adjustable. It will also help for a system to see whether it can do that task or not. So if I can give this knowledge to the system in some way, the Grakn way, then I can say, okay, can I do, if I know what my search task requires, then I can check whether I have LiDAR and I have GPS. And I can reason whether I can do that task or not. The same holds for the profiling. If I know what components I need to have for my profiling, and if all my software routines in this are okay or not, I know whether I can do profiling or not. So that's also something that we have implemented, which we'll talk about tomorrow. So we have components detecting whether the camera is on or off, and using a knowledge model in Grakn and some kind of rules and reasoning, can figure out, can I do profiling at this moment, yes or no? But that's still like a Boolean question, right? It's either true or false, yes or no. It's kind of simple. There's more gray area in it, because you might be able to do the task, but there's also a level of performance on how you can do that task. And we also want to be able to express that level of performance, on whether it's doing good, bad, worse, and so on. So for that, I will focus only on the profiling. And in this sketching configuration, I will have a camera and object detection algorithm that goes to a tracker. But as I mentioned, I can also track objects using my LiDAR. So that's an optional alternative. So for example, if I don't have a camera, I might use the LiDAR. If I really need my camera and my LiDAR is off, I can still do the profiling. Now, this camera creates images with a particular quality. This LiDAR creates particular scans with a particular quality. And so is my tracking output with a particular quality. The trick is, how can I specify that quality? Can I have some kind of a numerical expression for that, yes or no? And if I can, I say, okay, I have an output quality, I have an input quality, and the delta in between is specified by the performance of this entire configuration. So if I have good quality and bad performance, I will have bad output. If I have crappy quality on the input, I can have as good performance as I want. It will still be crappy over here. That's kind of like the reason that I want to put into the system. So as an example, we have a picture over here. Measures of whether that picture is of good quality or not are, for example, brightness and contrast. And this is a good quality picture, and this is a not so good quality picture. And that picture is sent into the object detection, and given a good quality input, I also can expect a good quality output, so that the actual system, the actual objects are detected that should be detected. I can measure that with a detection rate or a false alarm rate. If I have an image that is not so good, then I might be able to detect that that's a person, but not as specific as over here. And I might think that that's a truck instead of a Jeep. So this is just to illustrate the input quality and how it affects the output quality. And we also have implemented this into Grakn. So with these quality measures, which for the last, I think, 10 minutes I will give a bit more detail on that. So what we actually want to do is the system engineering knowledge that is out there, to model that into Grakn. I took a bit the wider picture of, or the bigger picture of this configuration. So I say, okay, I have a filtering configuration down below, and I have this awareness configuration. So I split the sensors with the processing routines. And, well, this is actually what we came up with. So, not surprisingly, a process has an input and an output. It has an algorithm. So we were having these triangular relations, and well, then said, okay, no, we don't need this triangular relation, we need a ternary relation. This is actually what we came up with. So, not surprisingly, a process has an input and an output. It has an algorithm. So we were having these triangular relations, and well, then said, okay, no, we don't need this triangular relation, we need a ternary relation. So we have our algorithm, which is the LiDAR detection or the camera detection, which has input, the laser scan, the pose or a camera image, and has an output, recognized objects, detected objects, which is going into another relation with an object tracking algorithm to return tracked objects. And that's the main model that we are using. So we are always constructing our system out of these processing relations with input, output, and component. And that's the basic, the main conceptual model for modeling the entire system. Of course, we need to have more because we have quality, performance, input, output, and so on. So these are attributes to those performances. So the camera image has a quality, which can be brightness, can be contrast. The camera detection also needs to know the environment because the environment will affect its performance. So that's either an attribute or a concept that should be related to that algorithm itself. Also, these ones will have quality, and this one also has quality. And that's also something that we have implemented into a system. We also have components that what do you call that? So basically, also use the image stream and process it to compute those contrast and brightness values. And we have implemented on that small car, and we just drove with the car. And our purpose was that this detection algorithm can detect 90 different things. But depending on whether it's outside or inside, it's more useful to specify already what you think it is should be detecting. So inside you will have persons, outside you will have cars, but it rarely happens that inside you will have a car, for example. So we used that internal assessment that I just showed to see whether we can recalibrate the detection component for a new environment. So if it was able to detect whether it was in a new environment or not, and if it was a new environment, that we can recalibrate on which labels it should focus. And in this case, we specified it all the way down to one label and one threshold. The results are not that great yet, but that's okay. So here you see that inside it's detecting all sorts of things. It's calibrating at this moment. And at a particular time it says, okay, in this environment I need to detect persons. And I'm using a threshold of 0.2. And then we drive around, which is our location, by the way. And then it can, for some reason, it detected a new environment. And it's again calibrating, and it says, okay, in this environment, I again should detect people. Then we go outside to the parking lot. It will also see here that's in a new environment and start calibrating and figure out that it has to focus on cars. And this is more or less the stuff that we are doing. There will be more detailed talks on how we model this into the system tomorrow. But for now, let me stop this. Oh no, there's one slide I forgot. Because we have some kind of a hierarchy over here, right? So I'm saying that these three components together, they form the awareness configuration. So also that is, we do that with the same kind of processing relation, and then we say that there is a membership relation to the components down below. So if we would have multiple configurations, we would know so that the system can reason whether to pick configuration 1 or 2, and what performance it can expect, because also all the attributes from the qualities over here are inferred upwards. And that's my final slide. So thank you.